basically, last time I described what happened before 2019, so what happened basically in all of the year of 2018. And so today I will try to connect with these observations and also try to explain you how quickly this field is actually moving and how many discoveries are being made every month right now. And basically, last time I had this slide which I prepared where I basically explained that correlated insulator states were observed in magic angle graphene next to its superconducting states, which may originate from these correlated states or may not. This is a debate right now. And today I'm gonna basically follow up on the story and explain that actually now we observe many more of these type of states in other integer fillings of the moire band. Then I also talked about or raised the possibility of strange metal phase close to these correlated states. And last but not least, a very recent development with these papers being actually published just a couple of months ago, or actually a couple of weeks ago at this rate, where we also observe magnetism and topological states. Okay, so, and basically this is the outline of the lecture. So first of all, I'll try to remind you of the main concepts we have right now for moire materials. I will then discuss the newly discovered correlated and superconducting states. This will be mainly also a discussion on my personal recent work in this field. And then last but not least, I will also touch base on some magnetic and topological states which have been discovered recently. And this will probably connect really well to Leon Balance's theoretical descriptions next week, which I'm also looking forward to attend because I will learn a lot myself. And also Leon is one of the theorists on the recent topological, on a paper which experimentally observes some recent topological states. So I'm also really excited to these lectures. So just a reminder again, so basically what happened in the last 15 years in the field is that we learned how to extract two-dimensional materials out of bulk van der Waals materials, so we can prepare single layers of graphite, which is graphene, but we can also prepare other materials such as insulators, semiconductors, and so on. We also learned how to make stacks out of these devices in a very clean way, so we can assemble these devices one on top of another, and we can create so-called heterostructures of van der Waals materials, in which it also falls the way we make twisted bilayer graphene. So twisted bilayer graphene is made out of two separate graphene sheets, which are then transferred one on top of another. These interfaces are extremely clean, and furthermore, of course, this gives us a new tuning knob. Starting from fully two-dimensional materials and combining them gives us a tuning knob of the twist angle between these materials, which is otherwise, I think, very hard to achieve in any other fabrication method like molecular beam epitaxy or pulse laser deposition and stuff like that. So this is, I think, very special to 2D materials. Okay, so, and basically, the whole trick was that if you transfer two layers of graphene one on top of another, and if you make a very sharply defined twist angle of only 1.1 degrees between those layers, the so-called magic angle, really interesting things happen, where K points between the top and bottom layer are basically very close in K space to each other, and they start hybridizing. And then people like Alan MacDonald have discovered that for very specific angles, flat bands are rising where the Fermi velocity basically drops to 0. And because now kinetic energy is quenched in the system, the Hamiltonian is mostly defined by the interactions, and all sorts of interesting interaction physics was expected, but now is also observed. Okay, so, right. So I wanted also just to show this video one more time because I thought it's really interesting. So this, again, the band structure of twisted bilayer graphene. We start at 3 degrees of misrotation angle. And actually, this band structure at 3 degrees is basically pretty much the same what you have for single layer graphene. So again, we have these, this hexagonal Brillouin zone. We have these Dirac-like energy bands, whereas we have two valleys in K prime, which are basically equivalent. And at even 3 degrees angle, these two layers are basically decoupled, and they're basically resembling single layer graphene. But then, as one reduces the twist angle, as you can see, the band structure becomes strongly renormalized, and then close to like 1.1 degrees, sharply at 1.1 degrees in this calculation, these bands here become extremely flat, and basically with a bandwidth of only about 10 MeV. Okay? All right. So, and the picture which is basically unfolding as of really late of 2018 is the following: that we have these two moire bands, the valence and the conduction valence bands, which each of which can take 4 electrons. Basically, it's a spin and valley degenerate. So therefore, if we start from the charge neutral point, which is where the Dirac cones meet and touch in this Dirac point, we basically can fill up the lower band with 4 holes. We can fill up the conduction band with 4 electrons, and basically once these bands are either completely empty or completely full, we have 4 electrons per moire lattice site. So 2 spin degrees of freedom and 2 valleys. Okay, so and basically these insulators, as I tried to explain last time, these insulators here are basically just band insulators. We get them from a single particle pictures. We don't take any interactions into account. The charge neutral point is again this Dirac point, where again no interactions are needed to observe this. And then basically what was observed as of last year was at a filling of -2 and +2 electrons per unit cell, correlated insulating states were observed. So where we basically observe very resistive states, and we can extract a temperature activated gap from, which again, we basically the most evidence why these are correlated insulated states is that they come at integer fillings of electrons, and also the other evidence is, or the evidence that it's an insulating state is because we can extract a temperature activated gap at low temperatures. And then flanking these correlated insulating states, there were left and right of it superconducting states observed. So basically, if we start from a correlated insulating state and we dope it slightly on the electron on the whole side, in both cases, you end up with a superconductor. And of course, this raised a lot of questions whether these superconductors actually inherit the phase of the correlated insulator, or maybe basically is similar to the cuprates. Maybe one possibility is that the correlations in the insulating state actually give rise to the superconducting behavior of these superconductors. Okay, so this was the picture as of 2018, and as you can see, there are stars actually at other filling factors. So why are these things not happen at a filling of 1, 3, or -1 and -3? So and actually, so as of this year, we started to observe these. Yep.
Why do you represent it? These are not symmetrical in your.
Yeah. So you mean why this is smaller than this? Yeah. So basically, if you look at the band structure, if I would follow this movie again, actually even from the single particle picture, the band structure between the hole and valence band is not symmetrical. So in principle, just even from without taking interactions into account, this would not be symmetrical. But then I think once we throw interactions in this thing, and once these energy gaps, etc., start to become sensitive of the Fermi energy and how many electrons we fill in these bands, then I think we're just not taking any symmetries into account. So we're not really expecting electron hole symmetry. And basically, as you can see, so I mean, this is not my personal data right now, but indeed the correlators they vary. The strength of the gap varies from electron to hole side, but also it varies with twist angle. So in principle, this type of diagram is rapidly evolving, and it's not like a general picture at this point. And also the superconductors we observed, they have different TCs. So and so far this one here has the highest TC. This is just, I think, empirically just what we observe. Okay, so, and basically, I guess basically the things which I was wondering is why does this happen at -2 electrons and +2 electrons and not like at -1 and -3? And indeed, really, if one recalls sort of the mod-like sort of representation of the bands, so this is basically, again, this single particle picture which we could have. So we have a valence band and a conduction band, and in principle, 4 electrons can sit in each band, which are degenerate by the k and k prime and by spin up and spin down. Okay, but in principle, so now with the picture which was demonstrated in the last phase diagram, one possibility would be that you could get bands at 2 electrons, so basically gaps at 2 electrons per unit cell. That would be a picture where, for example, one band is basically has 2 electrons per unit cell, and one of them is, for example, spin polarized, and the other one is spin polarized in the other direction. So in principle, these bands could have different spin textures, but also, of course, the other possibility is that they have different valence textures. So this is an active field of a study right now to really identify the ground states in these bands, but these are the possibilities. But of course, the other possibility is that we could also have this picture where we just have bands with 1 electron per unit cell, and it's valley and spin polarized at the same time. Okay, so and so these are the possibilities we have right now. So, and this is experimental data, which I also discussed last time. So again, what we measure in transport is just resistance as a function of carrier density. So we vary the filling in the bands just by applying an electric field to a backgate. And again, so these positions here, so these high resistance regions here are the band insulators. Then this is the Dirac point, and then these peaks here were the peaks at fillings of 2 and -2. And as you can see, resistance drops next to it, and we observed superconductivity. So okay, so and in my group, we basically tried to repeat these experiments, and we had a specific focus on making devices cleaner and cleaner. And so basically, this is now data which from devices of our group. As you can see, in first glance, it actually looks similar to this. So again, starting, so all the scales here are the same. So starting at the band insulator on the whole side here, we get band insulators. We also get a band insulator on the electron side. We get a Dirac peak in the center. And we get also the insulating states at -2 and +2. But as you can see, there are also other features arising, also at integer fillings. So we see a clear resistance increase here at -3, clear resistance increase at -1, which is completely missing in this work. And then the same thing happens at +1 and +3. So basically, what it seems like to happen is that actually we observe new correlated states, which now correspond not only to fillings of 2 and -2, but also to all of the integers, integer fillings of the moire lattice. Okay, so basically, at all of the filling factors, we observe resistive peaks, and basically, similar to the work by Pablo, we can also now try to do temperature activation of these resistance peaks, and we can try to extract the gap sizes in these. And indeed, again, what we do for this is we actually sit at the integer filling, we measure conductance as a function of temperature, and we plot it against inverse temperature. And basically, these straight lines here are basically exponential fits for the temperature activated gaps. And really, we can extract now insulating states at many fillings, so at -2, at +1 and 2, 3, and at actually a charge neutrality point and 0. And you know, they all have different varying sizes of insulating gaps, but these gaps are all below 1 MeV, so in principle they're very small. Yeah.
Just a precision, I mean,
Yeah.
a question.
Yeah.
So all this is zero field, zero.
At this point, it's zero field.
So
Yeah.
the filling factor is just, I mean, the number of electrons
Yeah.
per unit cell.
That's right.
moire
Exactly.
cell.
That's right. Yep.
Because usually, I mean,
Yeah.
I mean,
Yeah, it's not the quantum Hall filling. Yeah, it's not the quantum Hall filling, zero field. Yeah, it's electrons per unit cell. Yeah, that's right. Okay. Yeah. So and basically, and some of the states, some of this resistance peaks, we actually don't observe temperature activated behavior. So this could be because the gap is either too small, or the other possibility is that the interactions are actually not strong enough to actually open up the full gap, but they're basically just leading to some sort of Dirac-like semi-metallic transition. So this is also all possibilities from theorists. And so basically the -1 and -3 states, we don't observe an entire gap. And again, this is just, again, what we think is what's happening, is that we basically went from this picture to this picture, where we now are able to observe insulating states for every integer of electrons per unit cell, where we basically now start to get some bands where valley and spin might be broken at the same time. Okay, right. So, and now, as you can notice also, between some of the regions here, in regions between the insulating states, so in regions where the filling is not integer, but is some fraction in between the integers, as you can see also, resistance in many regions drops just basically to 0, right? So basically, between here, -3 and 2, resistance just goes to very low fields. And these are basically then new superconducting states which we observe. And the picture is now a little bit more complicated than just these two ideal superconducting states close to -2 and +2 filling. But we observe actually a variety of superconducting states. First and foremost, we observe these superconducting states which were not observed before. So and these are located in proximity to different correlated insulating states. So because here, for example, this superconductor is close to the -1 filling and close to charge neutrality. So this one is also between charge neutrality and +1, and this one is between +1 and +2. Okay, so all of these were not observed before. And also what you might notice here is that actually TCs of these bands are much lower. Much lower. So this superconducting pocket here, which is again also the superconducting pocket where Pablo observed the strongest superconducting state. In his case, TC was 1.7 Kelvin. In our case, we actually increased TC to 3 Kelvin now. And this is also the strongest superconductor here. But all the other ones, they're much weaker. Okay. So what we I'll come back later a little bit to discuss really the meaning and the evolving sort of understanding of these things. But first of all, really to convince you that we observe superconductivity, because this question comes actually every time we show our data. So the tests which we do for superconductivity is again all transport. So we measure resistance, nonlinear resistance, and we apply a magnetic field. And for all of these 4 superconducting pockets, we have done rigorous tests. And we really get TCs starting from 3 Kelvin all the way to 100 millikelvin. We extract HC2s, and we extract, for example, Xi, so is the coherence length, which is usually in the order of 20 to 50 nanometers. So it's usually the coherence length which we extract is several unit cells only. It's only 2 to 3 unit cells of the moire. Okay, so again, really this is just for you to check. So this is resistance as a function of temperature. So we get this linear temperature dependence for all of the states, leading almost to 100 millikelvin, which is again debated whether this is the strange metal phase. And then all of these states, the resistance drops to 0. Then again, we can do the following, that we can apply a perpendicular magnetic field. We can try to kill the superconducting state. And again, for all of 4 states, we observed that really by applying a field in the order of 300 millitesla completely lifts the superconducting state, and we recover metallic conduction. And again, sort of this linearity, which again could be the strange metal phase, it's fully recovered. So it goes, this linearity continues down to the lowest temperatures. So again, from these curves, we can extract a critical magnetic field as a function of temperature. We find that it's really well fitted with Ginzburg-Landau theory. And again, from these type of plots, we have extracted the coherence length. And last but not least, we measure nonlinear conductance, where we can show that really from nonlinear conductance, DVDI measurements as a function of carrier density, as a function of excitation current, we can really extract the typical critical current in the orders of only few nanoamps, actually. And from this, we can also show that this transition is very sharp, and it really is consistent with BKT transition and with two-dimensional superconductivity. Okay, so also, of course, we can apply a perpendicular field to the nonlinear conductance data, and we can see that the gap closes at 300 millitesla. So okay, and last but not least, okay, so our best evidence so far is this quantum coherence, this Fraunhofer pattern, which we can measure, which again is arises because we have still some very weak phase separation in the system, where the system just basically breaks down in Josephson junction in SNS regions. Okay, so and basically, so this is the phase diagram which we obtain, and basically now, of course, the question arises whether this phase diagram really has anything to do with that, or maybe this is now slightly different, and it really is more like that. Okay, so and basically, I guess what our study really adds up to the conversation is basically it fills up the other integers here, and we can basically position basically the same phase diagram at these locations, and we really get a phase diagram which now for every integer has a correlated insulating state. Also for the charge neutrality at filling 0, it has also, we observe a gap, and we think it's a correlated state here too. And then superconductivity, as you can see, arises in proximity to many of those correlated states, whereas I have to say these correlated, the bands, again, could have very different valley degeneracies and very different spin textures, etc. And therefore, in principle, if the superconducting states now originate from these correlated insulating states, also their ground state is potentially different. Of course, the other possibility is, now looking at a band structure, at a phase diagram like this, the other possibility is that maybe superconductivity just likes to be in the entire band, right? So in principle, there's like a huge density region where superconductivity was observed now. And of course, the other possibility, which is now also actively discussed, is whether maybe the flat bands itself like to be superconducting, independent of the correlated insulator states. Maybe this is something not related to the insulating states. Yep.
Do you see strange metal behavior in
yep.
each of these points? Above each of these superconductors?
We're preparing some data right now. Yeah. So we have the data, and we are preparing a manuscript. Yeah.
That speaks a little bit against the conventional superconductor.
Right. So I'm just probably try to explain all the different possibilities. I'm not trying to pick sides or so. And I think it is really possible that comes really from the doping of each individual correlated state. But also to answer your question, so this is for example temperature-dependent data taken for every superconducting pocket. So for example, this temperature-dependent data here, the red and yellow lines, these are from the states between 0 and 1, and 0 and -1. So these are the newly observed superconducting pockets. And as you can see, the temperature dependence leading to superconductivity is very linear. Down to temperatures of about 100 millikelvin. And even if we lift the superconductivity in the magnetic field, the temperature dependence in weak fields still continues to be linear there. So I think this is being sort of, they're basically controversial papers right now, one by the Santa Barbara group by Andrea Young, and the one by Pablo, which are both trying to explain this behavior in different ways. So Pablo is advocating the strange strange metal scenario, and then Andrea kind of had a paper out where they explained it all with phonons. Actually, Dasarma is the theorist on that. Okay, so but I think I'm not taking any sides, but this is all like in discussion right now.
And how does 8 Kelvin compare with bandwidth in this example?
So bandwidth again is in the order of 10 MeV, so it's below 10 MeV. That's right, yeah. So yeah, so that being said, so it's really just data. So this is what we measure in the lab, and then interpretation is a different thing. And by the way, this is sort of again based on our phase diagram. This is a review article on APS journal. So this is by Alan McDonald, where he also basically discusses all of the different possibilities which arise from these observations. Yeah. Oh, here. I think it was a mistake. Yeah. No, it should be there. It should be there. That was observed. Yeah. Yeah. Okay. So. Right. So and one thing I also want to this is more like an experimental fact is why I personally believe that we really went from this picture to this picture now is because I think we are starting to make better and better samples with less impurities, less inhomogeneities, and actually this picture here is in principle consistent with the previous picture, where again the strongest insulating features which we observe are -2 and +2, and the superconductor is close to -2. This is really consistent, so the energy scales are similar to what was reported before. And then the idea is that we really observe many more gaps which are much smaller. So all the superconducting pockets have much lower TC, more than an order of magnitude lower TC. Also the insulating state at +1 and +3, etc. They're much weaker, and they have we extract much smaller gaps. And so the idea is now that really we started to fabricate better devices. And as I tried to explain last time, in principle, graphene devices can be fabricated in a very clean way. So disorder and impurities is really not a problem here. But this is, for example, an STM image of a recent paper which just came out, I think, a week ago in Nature by the Columbia STM group. And so this just gives you a STM image of the device. And this STM image, you can basically see the evolution of the moire periodic potential as a function of spacing. So this is basically 20 nanometers here. So basically this whole graph is 100 by 100 nanometers. And maybe you can see that here the lattice constant is bigger than here, right? So something adiabatically changes in the device. And basically we think that a lot of the systems are very strained. And basically strain adiabatically evolves across the system. And basically what strain does is it basically changes the periodicity of the moire lattice very adiabatically and periodically. Okay, so and so of course if this region would be a magic angle, this would be something entirely different. And then here we wouldn't expect, for example, superconductivity to rise. So this is also where this phase separation in for the Josephson junctions arises. Okay, so and basically what we did in my group, we just tried to really improve this strain relaxation within the van der Waals stack. So this is a top image. This is basically an optical image of a typical stack which we are preparing. So there's a bottom HBN layer. This is a graphite backgate. Then somewhere here in the middle we have this twisted bilayer graphene. And as you can see, there's a lot of bubbles initially when we make these. And we basically found a way how to squeeze these bubbles out. We found a way how to release the stress and strain within the system. So we ended up in a we were able to remove these strain centers, and we ended up with a bubble-free device architecture. And indeed, so basically from our devices, we can measure the twist angle as a function of the whole device range. So this is So I will not go into detail, but from transport and from the position of the gaps as a function of carrier density, we can extract the twist angle between every region in the device by measuring different contacts in the device. And as you can see, so for a typical device we make right now, it's about 10 microns long, 2 microns wide, and the twist angle doesn't change really much. So I think this is within the measurement accuracy. So if we measure our device between these two contacts is 1.10 degrees, then between these two contacts is 1.12 degrees. But in principle, we think that we were able to smoothen out these strain variations, and therefore we believe we were able to observe much smaller gaps. Because in transport, again, yeah. That's right, yeah. So basically, usually if we measure here and here, for example, we get pretty much the same TC. Yeah. So it's relatively repeatable. Yeah. Okay, so in principle, now we're also making devices with many more electrodes, so we can test this more and more. Okay, so and so bottom line, I think the reason now we started observing other insulating states in the superconducting pockets is that we can now in transport resolve just much smaller gaps, which in more disordered devices are just washed out by these imperfections. And actually, 2 weeks ago, there were again free papers published on STM results. So last time I also touched base on STM results. So STM results are also local probes, so they can locally, in the cleanest region of the device, measure similar type of gate dependencies. So they can also measure the spectra as a function of carrier density, and they now all observe also these gaps at other integer fillings. But unfortunately, they don't do it yet, so they can really confirm the correlated insulator states, that they're all there. Unfortunately, STM hasn't gone yet to really the lowest temperatures yet, so superconductivity has not been yet studied with STM. So, but this will come soon. Okay, right. So one more thing, probably I will not discuss this in too much of a detail, but another thing is, so which we typically do in transport is we also like to apply really high magnetic fields and to measure Shubnikov-de-Haas oscillations, and Shubnikov-de-Haas oscillations typically give us some sort of idea of the underlying Fermi surface of these structures. So for example, this is typical quantum oscillations. So again, Shubnikov-de-Haas oscillation data which we're taking. So I don't know if anybody is familiar with these plots, because in our field everybody can read these graphs very easily, but I understand in a different field it's maybe more difficult. So basically the idea is that if we apply a large perpendicular magnetic field, so in this case we applied fields up to 5 Tesla, which is not too high for our means. Cyclotron orbits are formed, and the system is basically breaking down into Landau levels. And I'll just basically maybe try to explain this in this picture. So basically, Landau levels are formed in the system, and if you start with a Dirac-like equation, then basically by applying a finite magnetic field, you break the system into discrete Landau levels, which have all different energy, and basically. The number of electrons, which is in each Landau level, is basically determined by the size of magnetic field. Okay, so basically, if we apply a higher and higher magnetic field, there are more electrons occupied per Landau level, and this relation actually is surprisingly, but it's it's exactly linear with B field. Okay, so basically, if we measure now the data which I was about to show, so what we expect from Landau levels is to have a linear, Landau levels to be linear lines in this type of measurement. So again, so we measure resistance as a function of a perpendicular field, and as you can see from the different sort of integer fillings, we observe these perpendicular lines, okay? And basically, since these lines, each of these lines represents a different Landau level. Okay, so because the amount of carriers we can pump into a Landau level depends on the degeneracy of them. So if a Landau level is fourfold degenerate, if we again have valley and spin degrees of freedom, we can basically pump in 4 times more electron into a Landau level band than in a normal case. Then we can actually look at the slope of these Landau levels, and we can determine what the degeneracy of the underlying Fermi surface is. So basically, if we now start with the Fermi surface at 1/2 here, so this is the charge neutrality point we observe Landau levels fanning out to the left side and the right side, and if we closely analyze the slope of these Landau levels, we can show that all of them are fourfold degenerate. So this is basically just lines which we retraced here. So as you can see, all the Landau levels from the charge neutrality point is +4, -8, -12, -16. So they have a fourfold degeneracy, and therefore, again, valley and spin of the underlying ground state are conserved.
What are the -2 and +2?
We don't know.
Okay. Why did you say
So again, so for example, if it would be a ferromagnetic state, you would expect them to the degeneracy of 2. But the weird thing is, we observe -2, +2, but then we don't observe the two 2s to continue. So, but this is highly debated right now, whether these plus and -2 could eventually mean that the underlying ground state is ferromagnetically ordered. So you could have, for example, here at the conduction band, you could have, for example, a spin up, and here you could have a spin down ground state. But we don't observe any ferromagnetism here, so it's a debate. Yeah, but what we can say is that typically, this is also confirmed with other results, is that typically around charge neutrality we have mostly a fourfold degeneracy, but then if we look here, for example, at the -2 and +2 filling, we now observe a degeneracy of 2. So it follows the sequence of 2, 4, 6, 8, and also here -2, 4, 6, 8. So basically now here that means that some of the degrees of freedom is broken. So it's either valley or spin, right? And probably it points to where the picture where actually these states here, these bands here, are probably in a spin singlet, and maybe valley is broken. Okay, and then one can apply a magnetic field, and one can look at what happens to the insulating gap here. So because if you would have a spin singlet, you would probably expect that the gap in really high field would close. So you basically, Zeeman splitting just washes out the gap. Okay, but then reversely, if you would have a a polarized state, then the gap would actually open more, right? So these experiments are all underway, but they're, yeah. So for example, for the +1,4, in the case of Columbia, they actually observed that this insulating state becomes more insulating. Yeah.
Just one question about resolution. So
Yeah.
when you single out those Landau levels, you observe those without any ambiguity, right? But for example, is there any possibility that 6 or 10 are also there just with forward?
Okay, so I have to say also that this data, for example, this is really the real resistance values. So some people, I think in Pablo's case, they even took derivative, dr over dB, and some people even take second derivatives, to wash a sort of the more smoother modulations of the signal and to really get to the bottom of the Landau levels. So in principle, you can make these features sharper. And then you can tell quite accurately what's there, what's not. Yeah. Yeah.
I'm a little puzzled by those data from the following point of view. Here the moire lattice space is 14 nanometers.
Right.
So for example, at 4 Tesla,
Right.
you have a magnetic length that is roughly the same, even smaller.
Right.
Than the lattice space. So you should be rather in a Hofstadter butterfly.
Right. Yeah. We also, yeah. So actually, I removed that data line. So we actually see Hofstadter butterfly here. So the Landau levels start to cross, etc. And we actually now we have we just are also preparing a manuscript. So we made devices with much smaller twist angle, close to the second magic angle, where all of these bands are much closer spaced. And basically, we are in a regime where we can access 8 bands. So we have like a really complicated Hofstadter butterfly with 8 bands. But surprisingly, only very few states of them survive at high field. Okay, so, but this is, I can also discuss with you afterwards, and you know, but this is definitely, I think this is definitely underway. So I think for magic angle from 1.1 degrees, you still would want to go beyond 8 Tesla or so to really get into the Hofstadter regime. But for example, in the small twist angle devices, we get into the Hofstadter regime at like 2 or 4 Tesla. Okay. And so basically, and again, the story is also that here at the -3 correlated state, -3 corresponds to 1 electron per unit cell. We indeed observe a sequence of basically degeneracy of 1. So we see a -1, -2, -3, -4, etc. So again, this is not denoted here, but this is really, all of the degeneracies are there. So this must be some sort of state where both symmetries, basically it's either spin or spin and valley must be broken. Okay, so that being said, so now I'm probably getting a little bit off my comfort zone. So that being said, towards the end of the talk, I just want to talk about things which are not very clear right now. Okay, so basically we also observe, for example, here at the 1 and -1 insulating states, we also observe features which don't show any Shubnikov-de-Haas oscillations, so we don't think we see any Landau levels, but somehow the insulator itself seems to change its position depending in a linear fashion, depending on dn over dB, and if we try to look at the carriers which go into these states, we can basically assign a filling sort of 2 to this sort of slope here. And here also in the corner we see a slope which we can assign a filling of 1. And so basically the current evolving understanding of this, that these bands are potentially churn insulating bands, so where we basically can have possibilities of churn insulators with different churn numbers starting from 1, 2, 3, and -1, -2, -3. And there's a lot of theory work right now out there. And basically, interestingly, also along these churn insulating lines here, we also observe a superconductor to insulator transition. So in some locations, if we increase the magnetic field, so this is, for example, for the nu equals -1, if we increase magnetic field, we enter a region where we observe a sharp resistance jump, which basically, if we plot along this line as a function of temperature, we observe a superconductor to insulator transition. And interestingly, along this line in magnetic field, so if we sweep the magnetic field up and down, we also observe signatures of hysteresis, which is very narrowly located around the integer number here. So basically, if we go slightly to the hole or the electron side in doping beyond this state, hysteresis vanishes, and hysteresis is really the strongest directly at integer -1 filling here. Okay, so and basically the current understanding right now is that indeed this hysteresis vanishes with temperature. So we go about 1 Kelvin, this hysteresis loop completely disappears. The hysteresis also vanishes with density. So if we tune it left and right, hysteresis disappears if we go away from the integer filling. And basically the current understanding is that these states basically have something to do with potentially orbital ferromagnetism, where basically the underlying ground state is basically orbital ferromagnet at 0 field. And this orbital ferromagnet at 0 field can also induce a edge state, which again then corresponds to churn number 1 or 2 or 3 or whatever. And basically this state can survive at 0 field. And actually, so this was again recently reported by Andrea Young and by David Goldhaber-Gordon, where they basically can show that indeed they observe a hysteresis loop around zero field. Okay, so here is RxY data as a function of magnetic field. So they observe a hysteresis loop around zero field, and that hysteresis loop gives a quantized RxY signal where they really can resolve conduction conduction plateaus as H, which are exactly 1 H over E squared. And these quantization of these plateaus is really perfect to like a millionth, I think they reported in their paper. And so the general idea is really that at odd integer fillings, indeed one can have combinations where you could have potentially a topologically insulating state and a anomalous quantum Hall effect. Okay, so and this is really, I think these papers just came out like a couple of weeks ago, so this is really an evolving story. And I think this is also exciting because, again, beyond correlations, beyond superconductivity, beyond sort of all these super correlated physical phenomena. So now with the recent work, also correlation, magnetism and topology is added to the mix, and it's relatively observed in transport, in these type of devices. Okay, so the last sentence was corresponding to this slide, so I'll skip it. Okay, and basically, yeah. So I think this is it. What I wanted to tell you today. So Leon Ballens will talk more about these aspects, I'm sure, next week. And I hope without going to any theoretical explanations, I'll probably just prepare the ground for him and to really go into detail for next week. Thank you very much. You mean me personally, or? So okay. Oh, you mean all of these results? Okay. So so I can give you numbers. So topology is one device. Magnetism is now probably 3 devices and 3 different groups. So there are 3 groups. Right. Then strange metal. Again, I think all of us observe this linear temperature dependent. I think it's not a matter of data, it's a matter of interpretation. Superconductivity, this is maybe 3 or 4 groups, whereas Pablo's group, I think they by now have observed more than 10 devices. Superconductivity in my group, where we now have 3 devices which show superconductivity. Correlations, I think maybe like 8 to 10 groups have observed. But also, again, Pablo is statistically ahead of everybody. Pablo has the most samples, but I think, yeah, I think we'll see much more statistics in the next year. Oh, how do we go again? So the evidence is in the slope here. So the evidence we take is that also from a Chern insulator, you're expecting to have basically a behavior in magnetic field. So you can fill more electrons in it if magnetic field is increased. So this is sort of the only evidence. But I have to say, in this data, the evidence is really that you get topological conduction channels, which are perfectly quantized, and I think that evidence is of course much stronger. And again, so in this data this is from Andrea Young's group, as you can see, if you measure transport in this state, so Rxx goes to perfectly 0, Rxy goes to perfectly quantized, okay, and then you have this hysteresis loop against it. So it speaks that it's pretty good evidence that's the anomalous quantum Hall effect, and there, of course, you expect topological edge states. But then again, these states then have also slope in the n over dB. Yeah.
So the idea here is really that the anomalous quantum Hall effect and the fact that you find a churn insulator is intimately related to the fact that you have a symmetry breaking, time reverse symmetry
Right.
breaking arising from spontaneous ferromagnetism. Is that right?
So yes, yes. So it's all observed so far in the odd integer states as well. Okay, so it is very likely related to ferromagnetism. So, but again, in this case, the picture which is basically addressed to this at this point by some theorists is that it could be an orbital ferromagnet, because you in graphene spin orbit coupling is weak. Nobody ever observed magnetism in graphene, so from the carbon lattice, etc. So it must be some sort of more exotic ferromagnet.
But
Yeah.
I mean, flat bands are often
Yeah.
sufficient. So this is why you don't see it in usual graphene. There is ferromagnetism in usual graphene, but then it's implemented by the magnetic field.
Right.
In the sense that you form the zero energy lambda levels. So
Yeah.
you have a large density.
Okay, yeah, yeah.
And here it seems to be the flat band that replaces this.
Yeah, yeah. Capacity. So capacity, there was one paper by Ray Ashuri's group. So they're just next door to Pablo. So I think Pablo gave them the samples, but they can measure capacitance. Yeah, so as I said, I don't think anybody right now expects any symmetry in this system. Yeah. So there's for sure asymmetry, but also like from just transport you see asymmetry between everything, yeah. But capacitance, so there's again this group here at Santa Barbara, they're good in capacitance. Then in Pablo's case, they're doing capacitance. But yeah, but I don't think anybody really looked at the superconductivity or correlations in this regime yet. It's a little hard to do the experiment. Yeah. Oh, so okay, so right, so yeah, so okay, so this is still like a story in progress. So first of all, so that highest TC superconductor, this is the black line, and you see it's a very broad transition. Okay, very broad transition, and then you can see the superconductor close to filling 1, they're much sharper. Okay, so in principle, right, we observed superconductivity, we haven't actually gotten to analyzing and thinking about it. What maybe, again, maybe these are different types of superconductors, right? So they could be very different, and they could originate from very different ground states. And the other thing is probably here. So basically for all of the superconductors, again, we extract TC and BKT transitions. We extract coherence lengths, HC2s, etc. So in principle, from these numbers, one can maybe start to try to compare them. So for sure, the BKT transition in the free Kelvin superconductor is happens at much lower temperatures, and it's much more broadened as we see. And for the other superconductors, it's much sharper as well. It happens at.
Okay, if there are no more questions, thanks once more.
Thank you.